Alright, so in this video I'm going to go through the questions that you need to do to prepare for quiz 2. I've got alkali metals in here, which is what we're doing in the lessons at the moment, and then I've also got Avogadro's constant, which is from a calculations topic that you did last year in year 10, so it's part of revision that will help you with your mocks. So the first question is on the alkali metals. You're told that when you add sodium to water you get hydrogen gas, and you want to know what you would see. So if you're going to see if you're producing a gas, you're going to see bubbles. Another word for bubbles is fizzing. Another word for fizzing, that's actually here, is effervescence. So the answer is going to be effervescence, and that literally just means bubbles or fizzing, and that's what you see when a gas is produced. The next question, I want you to complete the balanced equation and add the state symbols. So you've got potassium K. What's the state symbol going to be? Well, potassium is a metal, and if it's a metal, it's going to be a solid. F2, they've already told you, is a gas. Then they ask you for KF. So KF is potassium fluoride, and you're told in the question that potassium fluoride is a solid. You then need to balance it. Okay, so I can see I've got 2 fluorines on the left. I need 2 fluorines on the right, and I balance using big numbers in front of the formula. By putting that 2 there, I now have 2 Ks as well on the right, and to get 2 Ks on the left, I need a big 2 there. So that gets you 3 marks. 1 mark for putting in the state symbols, and then 1 mark each for the balancing numbers. The next question is something similar. State symbols and balancing. So again, you've got sodium. Sodium is a metal, it's in group 1, so it's going to be a solid at room temperature. Water at room temperature is going to be a liquid. Okay, make sure you're not writing aqueous there. It's only aqueous if something's dissolved in water, but this is pure water. Then you've got NaOH, which is sodium hydroxide, and they tell you that's in solution. If something's in solution, then it's going to be AQ. And then you've got hydrogen, and you are expected to know that hydrogen is a gas. That is why we see bubbles. So hydrogen is a gas. State symbols get me 1 mark. Balancing again will get me 2. So it doesn't matter which one you start with. I'm going to start with oxygen. So on the left hand side, I've got 2 in front of my H2O, which means I've got 2 oxygens on the left. To get 2 oxygens on the right, I need a big 2 here. Okay. By putting that big 2 there, I've now got 2 NAs on the right. To get 2 NAs on the left, I need a big 2 here. I'm just going to double check that hydrogen is balanced too. I can see I've got 2 times 2. I've got 4 hydrogens on the left. And here I've got 2 hydrogens in NaOH. And I've got 2 hydrogens from H2. So in total, on the right hand side of the arrow, I've got 4 H's. And on the left hand side of the arrow, I've got 4 H's. So hydrogen is also balanced. The next question, they tell you that when you add lithium, sodium and potassium to water, you only see a flame of potassium, and they want to know why. The reason is potassium is the most reactive. Because it's so reactive, it gives off a lot of heat when it reacts with water, and that heat is enough to set potassium on fire. And when you burn potassium, it burns with a purple flame. You are able to light lithium and sodium on fire. They are flammable metals, but there's not enough heat given off when they react with water to actually set them on fire. So it's not true to say potassium is the only flammable metal. The other 2 are flammable also, but potassium is the only one that gives up enough heat when it reacts that actually it gets set on fire. The next question here is a 6 marker. Don't skip it, you have to do it. And you'll find a model answer for this in your booklet, and you'll also find the mark scheme if you scan the code, and you can see model answers there too. But I'm just going to highlight a few things. I'm not going to write out a full answer. You're asked how the teacher would demonstrate this experiment safely. You're also asked how the results give the order of reactivity. So there's 2 parts of the question, and both must be addressed. We're going to look at the safety part first. So if the teacher wanted to do this safely. So what they're going to do is they're going to take 3 metals, lithium, sodium and potassium, and they're going to add them to water separately. They are reactive metals, and when you're doing this reaction, you need to pay attention to how much metal you're using and how much water you're using. So the lithium, sodium, potassium are reactive. Okay, so I'm not going to take a massive chunk of potassium and throw it into some water. I'm going to use small pieces of the metal. we use small pieces of the metal. And because the metal is so reactive, rather than picking it up in my hands to drop it in the water, I might use a tweezers. Okay, a tweezers will be big enough because the piece of metal we're going to use is so small. So use the tweezers and add a small piece of the metal to the water. Now in terms of the water, okay, you might think to make the reaction smaller you should use less water, okay, but that's not true. It's the metal that's super reactive. It's going to give out a lot of heat, and if you've got lots of water, the water will then be able to absorb that heat. So we're going to use lots of water, so you're going to use, and rather than just using a little beaker or a test tube, you're going to use a large trough. You can write bucket, if that's easier to remember. You'll get the mark for bucket, although you won't see it on the mark scheme. Use a large trough of water. So it's just a big container full of water, and again, that's so the water can absorb the heat that's given out by this reaction. Other things for safety, you can mention wearing goggles, you can mention standing well back when you drop the metal in. You could use a safety screen, so just a piece of plastic in front of the trough where you're doing the reaction. So if you look at the mark scheme, you'll get all of the acceptable answers. You don't need all of them, you just need 2-3 points. Then you need to comment on how the results give the order of reactivity. So you can see for lithium, sodium, potassium, that potassium moves the fastest and it bubbles the fastest. Okay, now if you just copy the words directly from the table, unfortunately you're not going to get the mark. You have to interpret them. Okay, so I'm going from slow to fast to very fast. Which one is the fastest? Well, potassium. So I can say potassium bubbles the fastest. Don't say bubbles very fast. You say it's the fastest. It bubbles the fastest. You can also say it moves the fastest. And the reason is because it's the most reactive. You can then say that lithium moves the slowest, bubbles the slowest, therefore it is the least reactive. Okay, if you copy the words straight from the table, you're not going to get the marks. You have to interpret them and link it back to reactivity. Again, the mark scheme will show you every acceptable answer. Question 19 is on the same experiment. The first thing they want is to give the name of the container. Okay, so this is just a test tube. It's a small test tube. You can also call it a boiling tube. They're doing the same experiment that we just talked about above, and it said step 2 is unsafe. They said they're going to cut out 2 by 2 by 2 centimetre cubed of sodium. So that's just the size of the piece of sodium. If they're saying that that's unsafe and you want to change it, then you're going to use smaller pieces of sodium. Okay, that's going to be safer. Use smaller pieces of sodium, and then they ask you to explain why. And you can write so it will be less reactive, so that the reaction won't be as strong. Then they ask you to change step 3, and in step 3 they say they're only putting a few drops of water. So up here we mentioned that you want to use a large trough of water, and we're going to write exactly the same thing here. To make it safer, we're going to be using a large trough of water. And again, you need to explain why. You can't just say safer, you have to say why it's safer. You can say that the water can absorb the heat. Okay, so you say more, don't just write that. More water absorbs more heat. And that's what you're going to want to do, because lots of heat is going to be given out in this reaction. Down here, they give you symbols. They ask for a symbol of another element in group 1. So if you look at your periodic table, you find group 1, you'll see it goes Li, Na, K, and then after K you get Rb. So you can write Rb. Underneath Rb you've got CS, and then underneath that you've got Fr, and any of those will get you the mark. Just make sure you're writing the symbol and not the name. Atomic number of lithium, again you'll need to go to your periodic table for this. There are 2 numbers next to lithium, 7 and 3. The atomic number is the smaller of the 2 numbers. Just think atoms are small, atomic number is the small number. Describe the trend. Okay, when you're describing trend, you need to give me the direction of the trend. So I can see that melting points are getting smaller, but you have to say the direction. So they're getting smaller as you move down the group. All right, so you're going to write melting points decrease as you move down group 1. If you just said melting points decrease, you don't get the mark because you haven't given me the direction. The next one, explain in terms of electron configuration why they're getting more reactive. All right, so as I go from lithium to sodium, potassium, they get more reactive. You need to be able to explain why. So group 1 metals all react in the same way. They all lose 1 electron from their outer shell. And if potassium is the most reactive, it's because it finds it easiest to lose that outer shell electron, and you need to be able to explain why. So you'll say potassium finds it easiest to lose 1 outer shell electron, or 1 electron from its outer shell. You have to mention the outer shell, and then you'll say why. Because the outer shell electron is further from the nucleus. Okay, as you go down the group, they're getting bigger and bigger and bigger. You're adding 1 shell each time. And the outer electron, therefore, is getting further from the nucleus, and it's the nucleus that holds an electron into the atom. So if it's bigger and it's further away from the nucleus, there'll be less of an attraction. The next part is when we move on to the calculations. I'm going to put my iPad aside. Before we look at the exam questions, kind of a little bit smudged here. Before we look at the exam questions, we're just going to do some of the basics around this topic. So I appreciate that this is not an easy topic, but even if you're not able to get every mark on an exam question, I know that you will all be able to at least pick up 1 out of 2 or 2 out of 3 if you practice, okay? And I'm going to make this as straightforward as I possibly can, but you're going to have to stay with me and you're going to need to do the necessary practice. So we have come across words that represent numbers plenty of times in real life. So pair represents number 2, the word dozen represents the number 12, the word nil in football would represent the number 0, and then in chemistry we've got the word mole that represents the number 6.02 by 10 to the 23. Now you are given that number on your exam paper, and anytime they want you to use that number they will give it to you, so it's not something you have to learn off by heart. So how are we going to use that number? All right, well, if we look at a very simple everyday life example, all right, if I wanted to know how many individual shoes you had in 4 pairs of shoes, well, what would you do? Okay, you know that the word pair means 2. If you've got 4 pairs, you've got 4 times 2, and therefore you've got 8 individual shoes. Okay, if I were to change this and ask you how many socks in 4 pairs of socks, the fact that I've gone from shoes to socks doesn't make a difference. It's still 4 times 2. With this number here for moles, we're not going to be talking about shoes and socks, we're going to be talking about atoms. So the question might be, how many atoms in 3 moles of sodium? Well, I know the word mole represents 6.02 by 10 to the 23. If I've got 3 moles, I've got 3 multiplied by that number. And then you just need to pick up your calculator and you need to work it out. So it's going to be 3 multiplied by 6.02, and then I press this button here on my calculator to get by 10 to the 23, and then equals. And I get 1.806 by 10 to the 24. If I change this and said how many atoms in 4 moles of sodium, it would be 4 multiplied by that number. How many atoms in 0.5 moles? It's 0.5 times that number. If I change it from sodium to iron or from sodium to carbon, it doesn't affect the calculation. 3 moles of iron is going to be 3 times that number. The answer will be exactly the same, just as it was when I went from shoes to socks. There's another way that they ask the question, slightly harder, but we're going to do an example with buns before we do an example with chemistry. All right, so let's say, for example, you had 2 dozen buns, and on each bun you had 10 sprinkles, and you wanted to know how many sprinkles you had in total. Okay, you first need to know how many buns you actually have. Okay, if you've got 2 dozen buns, the word dozen represents the number 12. You have got 24 buns in total if you've got 2 dozen buns. If each bun has 10 sprinkles, you've got 24 buns, each have 10 sprinkles, you've got 240 sprinkles in total. Okay, we're going to do exactly the same thing but with a chemistry question. All right, I'm going to tell you that you've got 2 moles of CO2. Each CO2 is made of 3 atoms. I've got 1 carbon and 2 oxygen, so each CO2 has 3 atoms. How many atoms do I have in total? Well, up here, the first thing I wanted to do was work out how many bonds I had. And down here, the first thing I'm going to do is work out how many CO2s I have. So if I've got 2 moles of CO2, mole represents the number 6.02 by 10 to the 23. So I do that on my calculator and I get 2 by 6.02 by 10 to 23. I get 1.204 by 10 to the 24. All right, so that's how many individual CO2s I have. But I don't want to know how many CO2s I have. I want to know how many atoms I have. And each CO2 is made of 3 atoms. So I take this number, which is the number of CO2s I have, and I multiply it by 3 because that's the number of atoms in each CO2. So I times that by 3 and I get 3.612 by 10 to the 24, and that's the number of atoms. Okay, we are going to go to the exam questions to have a look. And the exam questions can be a little bit tricky. I appreciate that, but we are going to at least attempt them and at least pick up 1 mark of the 2, because the first mark is quite straightforward. All right, so at the top here, I'm just going to write down that it's always going to be number of moles, however many moles you have, and you're going to multiply it by that number. Okay, sometimes they won't give you moles, but we'll tackle that in a moment. Okay, number of moles times that number. All right, so the first question here says calculate the number of atoms combined in 1 mole of copper iodide. Okay, 1 mole, my number of moles is 1. Mole represents this number. All right, that tells me, okay, no, you don't technically need to write this out, but that tells me that this is the number of CuI2s that I have in total. But they don't want to know how many CuI2s I have, they want to know how many atoms. So this is the same as cakes and sprinkles. You now know how many cakes you've got, but how many sprinkles do you have in total? Here, I know I've got this number of CuI2s. I can see that in each CuI2 I have got 3 atoms. Okay, I've got 1 Cu and I've got 2 I, so I've got 3 atoms. So I'm going to take the number of CuI2s that I've got, and I'm going to times that by 3. I'm going to times it by 3 to work out the number of atoms that I have in total. And this works out as being 1.806 by 10 to the 24. Okay, and you get, I think, 1 mark for writing this out, and then another mark for working it out on your calculator. We're going to do the same with the next one. Okay, so it's always number of moles times that number, although unfortunately in this question they haven't told me the number of moles. What they've told me is the grams. Now, luckily, it's very easy to get from grams to moles. The formula triangle we used a lot last year was G Mr. moles. Okay, if I know the grams, and I do, and I know the Mr, and I do, it's here, 197, then I can find moles. So to use this triangle, I cover what I'm looking for, moles, and what I'm left with is my formula. So it's going to be grams divided by MR. And moles is going to be 3.94 divided by 197, and this works out as being 0.02, I think. 0.02. Yeah, so that's the number of moles I have. Okay, and once you know how many moles you have, you just use the number of moles times Avogadro's constant. Okay, times that big number. And again, you're given that number in the question. So you've got 0.02 times 6.02 by 10 to the 23, and you're going to work it out. So I'm just taking the number of moles, multiplying by that number, although this question, there was the extra step of finding moles first. All right. Next question down here, okay, again, they're giving me that number, so I know I have to use it. I know it's going to be number of moles multiplied by this number, but again, they haven't given me moles. Instead, they've given me grams, and they've given me relative formula mass. They've given me G, and they've given me Mr. They haven't given me moles. So again, that's the first thing I'm going to be doing. I'm going to be using G Mr. Moles to work it out. So moles is going to equal to the G divided by the Mr. I'm going to work that out. 0.11 divided by 44. I get 2.5 by 10 to the minus 3, and it's fine to leave that in standard form. Now I know how many moles I have, and then it's the number of moles times by that number. Alright, so that's what you're always doing. Number of moles times by that number, by 6.02 by 10 to the 23. And the reason this is worth 3 marks is you're told to give your answer to 2 significant figures. So you need to shorten it on your calculator to the following: 1.5 by 10 to the 21. So they're my 2 significant figures, the 1 and the 5 by 10 to the 21. The next one, again, calculate the number of oxygen atoms in 3.5 moles. All right, so I'm just going to zoom in on this part. This is the number of moles I've got. So it's going to be 3.5 multiplied by 6.02 by 10 to the 23. The way they word the questions can be confusing, I appreciate that, but if you just pick out moles from the question and multiply the number of moles by that number, you're going to get the first of your marks. If they don't give you moles, they'll give you G and Mr, so you find moles and then you multiply by that number. So here I'm after working out how many oxygen gases I have, and they do tell you that oxygen gas is the formula O2, so I have that many O2s in total. So how many atoms do I have? Well, each O2 is made of 2 atoms. If I've got this many O2s, I would then need to multiply by 2 at the end to work out how many oxygen atoms I have. Even if you didn't get the last part of that question, if you can get the first part, it's one of your 2 marks. So number of moles times that number. This next one is harder, but there are some marks that you can pick up, okay? You're given this number, so I know I have to use it. If I've got this number, I need to multiply it by the number of moles. Again, I'm not given number of moles, I'm given G, and I'm given the information to work out Mr, but you actually have to work Mr out this time, all right? So the other questions, they've just given you it, now you have to work it out. So if I'm working out formula mass, I need to have a look at the formula, okay? I can see in my formula I have got 2 aluminiums. There's an Al and a little 2, so I've got 2 aluminiums. Each aluminium has a mass of 27, so it's going to be 27 plus 27 for the 2 aluminiums. Next up, I've got sulfur, and sulfur is in a bracket and there's a 3 outside the bracket. That means I've got 3 sulfurs, because brackets mean multiply. So it's going to be plus 32 is for sulfur. I'm going to be timesing that by 3. And then I've got oxygen, and oxygen has a mass of 16. That's given to me there, but how many oxygens do I have? There's 4 oxygens in the bracket, there's a 3 outside the bracket. Bracket means multiply, so I've actually got 12 oxygens in total, all right? So that's the Al2, 2 aluminiums, that's the sulfur, and that's the oxygen. But you can see you've got 3 sulfurs, because sulfur is inside the bracket, and you've got 12 oxygens. 4 times 3 is 12. So I need to work that out and add it all up, so that's going to be 16 times 12 plus 54, works out as 342. All right, so you get 1 mark for working out your Mr. Now that I know Mr, I can use G Mr moles. Moles is going to equal the G, which they're given in the question, is 5.13, divided by the Mr is 342. 5.13 divided by 342, and that equals 0.015. So now I know how many moles I've got, and once I know how many moles I've got, I'm going to be timesing it by Avogadro's constant, by that number. So you're always timesing it by the number that you're given in the question, and you end up with answers 9.03 by 10 to the 21. Now, there's one more step, because that's the number of aluminium sulfates that you have, but you want to know how many individual atoms do you have, okay? And if we add them up, you can see you've got 2 aluminiums, you've got 3 sulfurs, so that's 5, and you've got 12 oxygens, so 5 and 12 is 17. You've got 17 individual atoms. You then need to multiply that by 17 to get the final answer. I appreciate that that is not an easy question. There are quite a few steps, but even if you can't get the whole answer, using G Mr. Moles, you should be able to find moles, and then it's always moles multiplied by that number. Okay, so these questions come up all the time, so rather than ignoring them, it is worth your while to be able to at least attempt them, even if you struggle to get the whole thing to work out.